In today's lesson, we're going to be looking at limits. To start us off here, when we're looking at limits, we're going to be looking at the first, what is the definition of a limit? Notationally, this is what it looks like. How you would read this, and that's usually the first thing that students want to know is, how do you read this? What is this saying? Well, it's read as the limit of f at x. So the limit of f at x as x approaches a, what does that equal? It equals L, some finite number in this case, is what we're going to be focusing on at first. So what a limit is essentially finding where the function is approaching, or what is it is equal to, as your x value approaches, in this case, some value a. So maybe x is approaching a half, maybe x is approaching 5, maybe it's 10, maybe it's pi, and where's that function f at x going or tending towards is what we want to find. Okay, let's look at some basic examples. So for this first example here, if you take a look, what we want to find is we want to find what is the limit as x approaches 1 of the function x squared. Well, the function x squared, what happens? As x approaches 1, let's say we're approaching 1 from the right-hand side, my function would be approaching, f at x would be approaching 1. As I approach 1 from the left-hand side, you can see that your function is also approaching 1 from below. So therefore, the limit as x approaches 1 of x squared is 1. Let's look at the next example. What is the limit as x approaches negative 2 of x squared? As I approach negative 2, if I'm approaching negative 2, let's say from the left-hand side, my function would be approaching 4 from above. If I approach negative 2 from the right-hand side, my function would be approaching 4 from below. So in this case here, the limit as x goes to negative 2 of x squared is 4. Now, an immediate question you might have is, what do you do if the limit as I approach one of these numbers is in different locations? Like maybe it approaches 1 and then from the left and 2 from the right. We're going to reserve that for a future lesson. So we're going to be focusing on situations like this, and we'll go from there. Okay, let's look at another example. So for this example here, we got another polynomial, and we want to examine what happens as x approaches 4. Well, as x approaches 4, if I'm going from the left or from the right, we can see my function is approaching 0. So the limit as x approaches 4 is 0. Now what happens as x approaches 0? Well, as x approaches 0, whether I go from if I go from the right-hand side, my function is approaching negative 4. As I approach 0 from the left-hand side, my function is approaching negative 4 from above. So therefore, in either case, the limit as x goes to 0 of f at x is negative 4. After these two examples, you might come to some conclusions. You make the observation here that to calculate the limit, I really just had to sub the 1 into here and the negative 2 into here to get these values. And likewise with this example, I just really had to evaluate this at f at 4 and evaluate this at f at 0. Well, there's a reason for that. Both of the two functions above are continuous functions. A rough definition of continuity, and we'll come to a more accurate definition later on in the course, is that a function is continuous if there's no holes or breaks in the graph. So if you have no holes or breaks in your graph, that makes for very easy limits. When you have that, you have these no holes or breaks in the graph, your function is continuous. And when it's continuous, we have some properties. One property is polynomials in general are continuous functions. The two examples we did above are fine examples of polynomials, but you can have higher order polynomials that might look something like this. Again, there's no holes or breaks in the graph. So wherever I go to evaluate the limit, whether I'm going to 2 or 5 or 10 or whatever, you can see whether you approach from the left or right, you're going to get that same value in either direction. So because of that, we have this following property that is very useful. If you have a polynomial, polynomials are continuous. So the limit as x goes to a of that polynomial is just the polynomial at a, right? So in the examples above, you noticed it would have been f at 4, f at 1, f at those values we were approaching would be the limit. In addition to polynomials being continuous, we can also apply that definition to rational functions. And when you're approaching rational functions, the limit as x approaches a of a rational function, in this case here, your rational function is polynomial divided by polynomial. That's going to equal the polynomial at a over the polynomial q at a. That's going to equal p at a over q at a, provided that q of a is non-zero. So let's look at some examples to see how that works. I want to evaluate the limit as x goes to 2 of r at x. So I'm going to let the top be p at x, polynomial, and let the bottom be q at x. Following our definition of continuity above, I know that q at 2 is going to equal, in this case, 2 squared minus 1 is going to be 3. That's not equal to 0. So because of that, I know that my function here, r at x, is a rational function, but I know that it's going to equal r at 2, right? Because, again, just to remind you, if you take a look at our definition, the limit as x goes to a of p at x over q at x is equal to p at a over q at a as long as that bottom is 0. Well, I've just verified here. The bottom is not 0, so this will just be r at 2, which in this case is 2 minus 1 over 2 squared minus 1 is a third. So for this example here, we're taking the limit as x goes to 3. So this is going to be the limit as x approaches 3 of x minus 1 over x squared minus 1. In this case here, you take the limit of the top and bottom. We're going to get 3 minus 1 over 3 squared minus 1 is 2 over 8 is a quarter. So in this case here, the limit as x goes to 3 of r at x is going to equal r at 3. And the reason for that is, you'll notice, just to remind you guys again, is the bottom, in this case the q at 3, was non-zero. So because it was non-zero, I could sub in that value, in this case 3, directly and get my answer. All right, let's try another. Okay, let's take a look at this example here. So I want to take the limit as x goes to 1 of x minus 1 over x squared minus 1. Now you'll notice in this situation here, p at 1 is going to be 0, but q at 1 is also 0. So in this situation here, as we evaluate that limit, we get 0 over 0. This is one of several forms of indeterminate form. So whenever you go to evaluate your limit and you do get 0 over 0, like we did in the previous example, typically that means there's some factoring techniques that have to be employed. Before we get to those factoring techniques, what I want to look at is some properties of limits, and then we're going to be able to tackle the question above. Here's 7 basic limit properties here. These are really important properties. We're going to use them quite a lot here. What they're saying here is f and g are continuous functions here, and with our examples currently, we should view these as polynomials or rational functions that are continuous. What it says here is that if you take the limit of the sum of 2 functions, in this case f and g, that's equivalent to taking the limit individually and then adding the result. Likewise, if I'm taking the subtraction, you can break that up and take the limit individually and then subtract the results. This example here is saying that if you take the limit of a function with a constant in front of it, you can actually pop that constant out and then evaluate the limit. This example here, we've got the limit of the product is actually the product of the limits. The limit of the division, you can take the limit of the top and limit of the bottom. Limits even go inside of exponents as well. So if you're taking the limit of a function to some power, you can actually take the limit inside and then raise it to that power. And likewise for radical expressions here, the nth root. Okay, obviously let's look at some examples, see this in action. Okay, let's take a look at this example here. I want to show you guys how rule 4 would work, for instance here. In this situation here, we're taking the limit of the product of 2 functions. In this case here, this would be my function f, and this would be my function g. So instead of having to expand this all out, simplify, and then take your limits, what you can do is you can take the limit of your first function, and you can multiply that by the limit of your second function. So in this case here, we would get, and because this is a polynomial, we can just sub those values in directly, in which case this is 3 times 1 squared plus 2, and 5 times 1 cubed minus 2 times 1 plus 1, giving us 5 times 5 minus 2 plus 1, and we have 5 times 4 is 20. So in this situation here, this is just one of the 7 examples here. Applying your limit property, when you're taking the limit of the product, you can take the limit individually and multiply those results. Likewise here, let's take a look at an example for property 6. Let's say you want to take the limit as x goes to 1 of 3x squared plus 2 to the power of 10. Again, you don't want to raise this to the 10th power and have to expand it all out. What you can do is take the limit inside. So this is going to equal the limit as x goes to 1 of 3x squared plus 2 to the power of 10, which is going to equal, now we can evaluate that. That'll be 3 times 1 squared plus 2 to the power of 10 is 3 plus 2 to the power of 10 is 5 to the power of 10. Take note of these limit properties. We're going to be using these throughout, and it'll just be second nature. We'll use them quite a lot. And so study these two here, and you can make up your own if you want to try the other ones here. And I'll make note of when we use these properties throughout the next several lessons. Okay, I want to take a look at a limit here. What I was saying earlier is if you go to evaluate a limit, in this case this rational function, notice if I go to sub this value of 4 in, we get a denominator equal to 0. So we can't continue. But this is in indeterminate form. We have 0 over 0. When that happens, that means there are some factoring techniques that have to be employed here. So I think most of you guys can see here, if you take a look at this situation, we want to evaluate the limit. I am in indeterminate form. You look to see, can I factor this? Well, in the numerator, you can say I can break this up into a difference of squares. And now what happens here is I'm going to take the limit as x approaches 4. X is approaching 4. It's never actually hitting the value of 4. So because of that, because we're approaching 4 and never actually being exactly on 4, these x minus 4's can cancel. They're non-zero values. They can cancel. And this ends up being the limit as x goes to 4 of x plus 4. Now you'll see here we're left with a polynomial. I can sub it in. Polynomials are continuous. This becomes 4 plus 4, and the answer is 8. Let's look at another. So for this question here, we have a similar situation. If I go to sub that 2 in here, you end up getting 0 in the top and 0 in the bottom. Because of that, this is an indeterminate form, and we're looking to see, are there some factoring techniques I can use to break this down and get something like what happened in the previous example? Well, you're going to notice here in the top here, we have a difference of cubes. If you've forgotten the difference of cubes formula, it's right here. And in the bottom, we have a simple product sum. So this will break up into the limit as x approaches a of x cubed minus 2 cubed over, this will factor into x minus 2, x minus 1. Continuing on in this way, here we have the limit as x goes to 2. Using our difference of cubes formula, we have x minus 2, x squared plus 2x plus 4 over x minus 2, x minus 1. And now to remind you again, we're taking the limit as x approaches 2. It never equals 2. And because of that, we can cancel these off. And in which case, this becomes a limit as x approaches 2 of x squared plus 2x plus 4 over x minus 1. Now, if you take a look here, I can sub in this value of 2, and I'm not dividing by 0. And because I'm not dividing by 0, we know we have a continuous function at this value here. And that's a key point. It's continuous at this value. And therefore, we end up getting 2 squared plus 2 times 2 plus 4 over 2 minus 1. And we get 4 plus 4 plus 4, which is 12. So the limit as x goes to 2 of this expression, of this rational function, is 12. Let's try another. So same idea for this one here. I'm taking the limit as h goes to 0. As h is approaching 0 here, you'll notice we end up once again getting that indeterminate form. And when that happens, now this becomes a question of factoring. Well, how can I factor this? Well, this is the limit as h goes to 0. I can rewrite the 4 as a 2 squared, divide by h. And in this case here, it's a limit as h goes to 0. We have difference of squares in the top, so we have 2 plus h minus 2, 2 plus h plus 2, and the whole thing over h. And you can see here, in this case, the 2's will cancel. We have the limit as h goes to 0 of h. Notice the 2's here will cancel. You're just left with a factor of h here. Collecting like terms inside the brackets. The next product, we get 4 plus h over h. And again, we're taking the limit as h goes to 0, approaches 0, not equaling 0. And because of that, you have a non-zero number that is the same the top and bottom. In this case, the h value, those cancel. And now we have the limit as h goes to 0 of 4 plus h, which is equal to 4. Let's try another. So this question here, we're taking the limit as x goes to 0. Once again, sub it in that 0, you're going to get 0 over 0. So we're in indeterminate form here. In this situation, to figure out how to cancel off, like if you're in indeterminate form and I'm getting 0 divided by 0, there must be a factor that's similar in the top and bottom here. So I need to cancel off this x. I need to be able to cancel off this x. When you sub in, if I sub in a 0 in this case and I get 0 over 0, that means that there's a root of 0 in the top and a root of 0 in the bottom, which means that there is an x in the top and x in the bottom that we can cancel off here. So I have to get at this x value. So what I'm going to do is I'm going to rationalize the numerator. So to rationalize the numerator, what you do is you multiply the top and bottom by the root of x plus 1 over the root of x plus 1 plus 1. And we have the limit as x goes to 0. What we have here in the numerator here is difference of squares. So this ends up being, notice the roots cancel, this ends up being x plus 1 minus 1 squared over x times the square root of x plus 1 plus 1. And we get the limit as x goes to 0 of x plus 1 minus 1 over x times, again, I'm just going to leave this all together. I don't want to expand this out, and the reason for that is when I go to evaluate this limit here, I want those x's to cancel, and look, they do. You'll notice here we've got the limit as x goes to 0, approaching 0. These x values will cancel off as intended, and now I'm taking the limit as x goes to 0 of 1 over the root of x plus 1 plus 1. And now you'll notice here, although these are not polynomials, I know that I can take the limit of the top and the limit of the bottom, in which case we get the limit as x approaches 0 of 1 over the limit as x approaches 0 of the root of x plus 1 plus 1. And again, you'll notice here we're applying a lot of our limit properties. So the limit as x goes to 0 of 1 is just going to be 1 here. So this will be the limit as x goes to 0 of x plus 1 plus the limit as x goes to 0 of 1 is going to be 1 over the square root of, this is just a polynomial, so that's going to be root 1, that's going to be 1, and you end up getting a half here. Now you can see the limit operations and properties. I used several of them here. In this case here, going from this line to this line, I knew that the limit of a quotient, you could take the limit of the top and the limit of the bottom. The limit as you approach a constant value is always just that constant value. In this case here, the limit of the sum is I can take the limit individually, and I also drop that limit inside the square root. That was property 7. And then I went to go take the limit of x plus 1, and I just subbed that 0 in directly because it was a polynomial, it's continuous, and we got a half. Let's try another. So for this problem here, again, we're getting that indeterminate form, looking for some factoring techniques here. Well, right away, you're going to see we have a difference of squares in the top. So I can change this to x squared minus 1 times x squared plus 1 over x minus 1. Notice I sub the 1 in at this point. I still get 0 over 0. So I'm going to have to go ahead and factor this some more. So this becomes a limit as x goes to 1 of x minus 1, x plus 1, x squared plus 1 over x minus 1. Just doing our difference of squares formula, in which case here now these factors cancel off. X is approaching 1. It's never equal to 1. So x minus 1 over x minus 1 is, you can cancel that off. In which case here we get the limit as x approaches 1 of x plus 1 times x squared plus 1. And that's over 1, so I'll just leave it like this. And now again, this is applying more of our limit properties here. We're taking the limit of the product of two terms. I can take the limit individually, but the insides are just polynomials. So you're just going to end up subbing them in anyway, and this becomes 1 plus 1 times 1 squared plus 1, which is going to be 2 times 2, which is 4. All right, let's try another. In this example here, we want to evaluate the limit as 4 plus h to the power of 3 minus 64 over h goes to 0. So notice they changed the variable h here. Again, it doesn't always have to be an x. So the deal with this one here is the same idea. If you put a h equals 0 into this, you get 0 over 0. 4 cubed is 64. So because you get a 0 over 0, there must be a factor of h in the numerator and denominator. So we have some factoring techniques we have to use. Taking a look at the top here, we've got a difference of cubes I could set up. So this will be equal to the limit as h goes to 0 of 4 plus h cubed minus 4 cubed over h. And again, just as a reminder here, we know that x cubed minus y cubed factors into x minus y, x squared plus xy plus y squared, which means that this will be the limit as h goes to 0 of 4 plus h minus 4 times 4 plus h squared plus 4 plus h times 4 plus 4 squared, and that whole thing is going to be divided by h. Now we're going to continue our limits. This is a limit as h goes to 0. Now notice here the 4's will cancel, and I'm just left with that h that I wanted. I'm not going to go ahead and expand all this out. I'm just going to leave it in this form because we're going to end up taking the limit as h goes to 0. And again, because h is approaching 0, it's never equaling 0. These h's will cancel off, and you get the limit as h goes to 0 of 4 plus h squared plus 4 times 4 plus h plus 16. And now the idea here is we have a polynomial. It's continuous. I can sub in this h here of being 0, so this would be 4 squared times 4 plus 16 is 16 plus 16 plus 16, and that's going to be 48. Okay, let's take a look at another. So for this question here, we want to evaluate the limit as x goes to 4 of this expression. Right away when looking at this, you want to make this look simpler. So right away I'm going to go ahead and get a common denominator in the numerator, in which case this will be 2 minus root x over 2 root x. Take that entire expression and divide it by x minus 4. So now we have fraction divided by fraction, right? I can put this over a 1, and now you have fraction divided by fraction. And when you have fraction divided by fraction, if you remember, you can multiply by the flip. So this would be 2 minus root x over 2 root x times 1 over x minus 4. And we end up getting the limit as x goes to 4 of 2 minus root x over 2 root x times x minus 4. Now in this situation here, what we want to do is I'm looking to cancel off the variable here. In fact, you'll notice with this original question, if I sub in a 4 here, we get 0 over 0. Because if you sub in a 4 and you get 0 over 0, that must mean that there is a factor of x minus 4 in the numerator and a factor of x minus 4 in the denominator, which is obviously this one. That'll cancel off. So that's a good tip and hint as to know what factoring techniques to use. So I'm going to go ahead and I'm going to multiply the top by 2 plus root x, the bottom, times 2 plus root x. And I end up getting here the limit as x goes to 4 of what we have here is a difference of squares. So this will factor, or expand, I should say, into 4 minus x divided by 2 root x times x minus 4 times, don't forget that 2 plus root x in the bottom. That's still part of the equation. So now we're here. Now you'll notice here, these two factors are not exactly the same. However, I can take the limit as x goes to 4. I can factor out a minus sign. That becomes x minus 4. Then we've got our 2 root x. There's that x minus 4 I want to cancel, then plus 2 root x. So now if we continue here, we're taking the limit as x approaches 4, never equals 4. So these are non-zero terms. I can factor those out, cancel those off. And I end up getting negative 1 over 2 root x times 2 plus root x. Now you'll notice here I can sub in that 4, and there's no indeterminate form on that. And subbing that in, we end up getting negative 1 over 2 times root 4 times 2 plus root 4, which is negative 1 over 2. This becomes here, if you notice here, this is 2 times 2. That gives you 4. And this is 2 plus 2. It also gives you 4. So that ends up being 16. And we get negative 1 over 16. Okay, that concludes the lesson. I definitely encourage you guys to re-watch this lesson. Pause. Try to work through the problems on your own now. Make notes of where your issues lie, and keep in mind these are several factoring techniques that we're going to use over and over again. So definitely study these. You've got here your difference of cubes. There's also a sum of cubes technique, the idea of rationalizing the numerator. So study all these limit techniques. We're going to come back to them over and over again. Thank you.